Hello everyone. So today in the session, we are going to see the concept of the minimization of switching functions. So this is the regarding of second unit. So let us see the contents, what we are seeing here. So the contents are nothing but the topics what we are going to cover in the second unit. Okay. The first topic will be the K-map method, which is nothing but Karnoff mapping method. So you can call this K-map method, or in other words, as an witch diagram. So while you are dealing with the concept of K-map, we will come across these prime implicants as well as the don't care combinations and as well as this minimal SOP and POS forms. Okay, so these four will be covered in the part 1 of the second unit, and this fifth and sixth, seventh topics, that is nothing but Quine-McCluskey method, which is called as tabular method. So while you are dealing with this method, we will come across the prime implicant chart as well as the simplification rules what we are going to follow regarding this particular table method. Okay. So the first four topics include your part 1 of the second unit, and the remaining 3 topics will cover in the part 2 of the second unit. Okay. So today we will discuss the first introduction of the K-map and how K-map is used and in which conditions K-map is going to be used. Okay. So before we see that, so the previous unit we have seen, like, so we already know how to simplify an SOP and POS expression, right? So, the basic conditions that we need to remember in nothing but the first thing is we need to minimize the literals. Okay, we need to minimize the literals. So if you minimize the literals, obviously you will get minimum number of terms in your expression. Okay, the ultimate goal of a designer of digital circuit is to reduce the number of terms in a final expression as much as you can. Okay, so if you start minimizing the number of literals, obviously it will reflect the reduction of number of terms in your expression. Okay, right? So these two are the basic. Okay, these two are the basic criteria for us in order to achieve the better results. Okay, first of all, you need to minimize the number of literals, which internally it affects the reduction of the number of terms. Okay, clear? And now, so till now we have seen how to what we can say, uh, how to reduce the SOP expression or POS expression till now, and now we will see what are the techniques we are going to see. See the first condition in the previous what we can say previous unit, you have learned how to reduce the what we can say an expression, how to reduce the expression with respect to uh, the number of terms that is going to depend on function. Okay, so you have learned them. That means you have learned how to reduce algebraically, right? Algebraically means by using the properties as well as theorems present in the Boolean algebra. So we have several properties like associative property, commutative property, like distributive property. Like that, we have some more properties. And when coming to theorems, we have a duality theorem, likewise consensus theorem, and then we have a De Morgan's theorem. So by using those theorems and properties, we know how to reduce. So if you use the properties and theorems for reduction of SOP or POS expression, you call that as an algebraic method of reduction. Okay, we call it as an algebraic method of reduction. But if you follow this algebraic method, it is only suitable for a minimum number of terms. That means if you are writing an output expression f equal to, right, f equal to some an expression, suppose if the expression consists of five terms, then it is easy to apply the properties and theorems on this. Okay, it is easy to apply properties and theorems on this. But for example, if you consider that if your expression f is equal to, if it is consisting of 20 terms or more than 20 terms or more than 10 terms, okay, more than 10 terms or more than 20 terms. So when an expression consists of 10 or 20 terms, then in this concept it is very difficult to apply theorems and properties, right? So in order to overcome this problem, That means when you have more number of terms involving your expression, then this algebraic method is not satisfied, or it may not give an effective result for us, right? So what I'm saying here, moving from this method to the second better method called as K-map method. Okay, we are moving to this K-map method. So what is K-map? K is nothing but Karnoff. He is the mathematician who proposed this method, right? So Karnoff is a mathematician who proposed this mapping method in order to reduce a Boolean expression. Okay, so this K-map is also consisting of some limitations. We are having some limitations. In order to overcome those limitations, we are again going for new method called as tabular method, that we will discuss later. But now, the first method, algebraic method, is not sufficient for us, or not efficient for us when the condition is this one. It means if we have more number of terms, this algebraic method cannot be effectively working for us. That's why we are moving to the K-map method, the new technique called as K-map method. Okay. Now we will see the K-map technique, right? Okay. See here. See. So in general, the K-map is nothing but this Karnoff mapping is purely depending on the concept of logical adjacency. It's very important. In K-map, we prefer or we work on the principle called as logical adjacency. So what is adjacency? They should lie side by side. Okay, they should lie side by side. Okay, side by side. Adjacency means side by side, or else we can say it as the particular K-map should satisfy the adjacency property, which means that the cells or the numbers or the terms present in the K-map should lie side by side. Okay, so you can say that based upon this logical adjacency, the K-map starts working. Okay, just to remember, this is the basic principle what we are going to use. This is the basic principle we are using in the K-map. Okay, now, okay, see, this is the main introduction and the starting of K-map. So follow this carefully, right? So if you see this, generally the K-map is nothing but it is a two-dimensional representation of an truth table. So what is a truth table? So truth table is nothing but, okay, truth table is nothing but the table in which it represents the input combinations with respect to their output values. Okay, the table which represents the input combinations with respect to their output values. So you can call it as a truth table, and you can represent the same truth table in a two-dimensional way. So this two-dimensional way is called as, we call as a K-map. Okay, so here also it, see here also I mentioned same point, the logical adjacent terms. The logical adjacent terms are physical adjacent in the K-map. Okay, the map is nothing but it is a word. Map is nothing but it is a word where we can analyze the behavior, or we can analyze the terms, which is easily helpful for us to analyze the operation of circuit, right? So in general, what we will say, map nothing but it will convey some information, right? It will convey some information which is easy for us to understand. Likewise, here also this K-map is helpful for us to analyze the SOP or POS expression easily, and they help us to simplify them easily, so that you can attain or you can achieve their uh, respective output with the less number of terms. Okay, the reason behind this is nothing but our main task is to get the less number of terms in the result. So these logical adjacent terms, the logical adjacent terms will help us to, okay, this will help us to get the less number of terms in the result. Okay, so this K-map will contain the boxes or a small squares which is called as a cells. It's very important. Okay, it contains a boxes or a small square which is called as a cell. Okay, clear now. So each and every cell will represent one of the 2 power n combinations. As we know that for n number of variables, we will have 2 power n combinations. We will have 2 power n combinations. That means the table will entirely represent all the 2 power n cells. Okay, the K map entirely will represent all the 2 power n cells. Among that, each and every cell will represent one of the 2 power n. That means any one among the 2 power n will be represented by each and every cell. Okay, so therefore, for n number of variables, we will have 2 power n number of cells. Okay, okay, remember that for n number of variables, you will have 2 power n number of cells. Okay, this is the important point. For n number of variable K map or n variable K map, there will be 2 power n cells, right? So see here, I have represented here 4 ways or 4 K maps, and each and every K map will represent one model. See, suppose if you are taking an one variable K map here, so as per the condition, for n number of or n variable K map, you will have 2 power n cells, right? So likewise, if you take one as the question, one as n, you will have only 2 cells. So one variable means I took that variable as x for the time being. So if it is only one variable, we have only 2 combinations. That is, one is 0 and one is 1. So x may be 0 or x may be 1. So one cell is for 0 and one cell is for 1 condition. So we are having 2 cells. So you can call this as an one variable K map or 2 cell K map. Why? Because we are having 2 cells here. So you can call it as an one variable K map or 2 cell K map. Okay. Likewise, if you take 2 variable, that means small n value equal to 2, then you will have 4 cells. This is first cell, second cell, third cell, fourth cell. Total we are having 4 small boxes. Okay, each and every box, see, this is called as cell, this is called as a cell, so this is called as a, so each and every small box present in that is called as your cell. So as I'm having two variables here, so I will take the first variable as the row and second variable as the column. Okay, so x is again taken as 0 for one row and 1 as the another row. Y is taken as 0 for the one column and y is taken 1 for the another column. Okay, so like that you can label the rows and columns with respect to the inputs given. Okay, therefore this particular cell is the combination of this row plus this column. So this particular cell is something, but it is combination of this row plus this column. Like that you can analyze the working operation of this one. Okay, just to learn the structure of K-map, how to draw a two variable K-map. You can call this as a two variable K-map or 4 cell K-map. Why? Because we are having 4 cells here, right? Next, go for the 3 variable. If it is 3 variable, the first variable should be assigned for rows and the remaining 2 should be assigned for column. Very, very important. The first should be assigned for row and the remaining 2 will be assigned for columns. And as usual, I am having only single variable. X may be either 0 or x may be either 1. That is already we know. Now, so how to label the column values? As we are having 2 variables involved in a column, here we come across the gray code mechanism. Okay, here we come across the gray code mechanism. Always the label of the columns or rows where 2 variables are involving should be given with the gray code system. So what is gray code system? In general, what is the sequence we are having? If 2 variables are there, we are having 0, 0, 0, 1, 1, 0, and 1. These are the 4 combinations we have when we use a normal binary system. But it is not binary. They are asking to follow the gray code. They are asking to follow the gray code. So what is gray code? If you convert 0, 0 into gray code, you will get 0, 0 again. If you convert 0, 1 into gray code, you will get 0, 1 again. But if you convert 1, 0 into gray code, you will get 1, 1 here. And if you convert 1, 1 into gray code, you will get 1, 0 here. And now you are asked to take this into the consideration, take these values into consideration. That's why I took first 0, 0, next 0, 1, then 1, 1, and last 1, 0. Okay. This is the values what I have taken regarding the gray code system. Okay, clear? So this is the gray code values and this is normal values. We have assigned them rows and columns. Total we are having 8 cells. Okay, why? Because it is a 3 variable K map. Okay, 2 rows with 4 columns. Total we have 8 cells. Okay, you can call this as an 3 variable K map or 8 cell K map. Both are same. Likewise, we go for the last one, 4 variable K map. So what is 4 variable K map? For n variable to 4 n cells. For 4 variable, it will be 16 cells. So 4 rows, 4 columns. The first 2 inputs will be assigned for rows. The next 2 inputs will be assigned for columns. So same as I am having 2 input variables involving in the rows, I should follow the gray code mechanism. Likewise, here also I should follow the gray code mechanism. Okay. Recently, we have seen what is the gray code sequence: 0, 0, 0, 1, 1, 1, and 1, 0. Likewise, here also 0, 0, 0, 1, 1, 1, 1, 0. So, like that, you should label the rows as well as columns, right? So, you can call this as an 4 variable K map, or we are having 16 cells, so it is called as a 16 cell K map. Okay, clear? So now we will see clearly what is each and every K map. Okay, now see the first one, it is an 2 variable K map. So I draw a 4 cells like this, and I assigned first input for the row, second input for the column. In the row and column, I am having only one variable involving. That's why I return 0, I return 1 for the label of rows. I return 0 here, 1 here for the label of columns. So I labeled them clearly. Now, if I want to write the address of this cell, what is address of the cell? The value of row and the value of column. If you combine them, it will form an address. Okay, remember that always the row value followed by the common value. Okay, row value followed by the column value will give the address. Okay, what is row value here? 0. What is column value? 0. So 0, 0 is the address of the first cell. Like that, go for second cell. Row value is 0, column value is 1. I am saying about this one. Okay, row value is 0, column value is 1. So when you combine them, 0, 1 will be the answer, and that is the address of the cell. Like that, be clear that first of all you should write the value of row, then you should write value of column. Then only it will form an address of the cell. Okay, you should not write column first and row second. Okay, the sequence should be like this: row value followed by the column value. Okay, right? Next step. So see here. So after writing this, you can represent the same diagram either in SOP or POS. Like SOP or POS. Suppose if I am taking SOP as my consideration. So what is the assumptions we are going to take in SOP? Any literal whole bar is taken with 0. Suppose if literal is not a complementary form, that is it is true form, then that should be taken as 1. So these are the two assumptions that we are going to make in case of SOP, right? So by using these two, we can substitute this 0, 0. Here x is 0 as well as y is also 0. So x in terms of 0 is x bar, y in terms of 0 is y bar. So the first cell will be replaced with x bar into y bar. Likewise, you can fill up all these remaining values. Next, you can convert the same diagram into M notations also. What is M notation? As we are dealing with SOP, always you will have min terms. Always will have min terms. Okay, min terms. So, what is a min term? Each and every product term in SOP. Each and every product term in SOP is called min term. So, the notation is given with the small m. Okay, small m. And for each and every m, we find here small 0, small 1, small 2, and small 3. What are these? These are called as an index numbers. Suppose if you are writing like M3, M suffix 3, this 3 is called as your index number. So how will you get this index number? Convert these address values into their respective decimal numbers. Okay, convert these values into decimal numbers so that you will get index numbers. Okay, convert these address values, binary address values into the decimal form, you will get the index values. Okay, and remember that the index value represents your cell number of, okay, it represents your cell number. Okay, so what is the cell number of the cell? 0. Always your cell number should be written in the right side bottom corner. So 0, 1, 2, 3. Okay, index numbers and cell numbers both are same, and always your uh, cell number should be written at the bottom right side bottom corner of each and every cell, like this should write. Okay, clear? Suppose if you take the case of a POS, then you will get here capital M0, you will get here capital M1, you will get here capital M2, and you will get here capital M3. Okay, index values will not be changed. Why? Because address values will be constant, therefore index value will be also constant, only the notations will be different here. Okay, next go for the verification of 3 variable. The same concept here, 3 variable, same. I took the first variable as my row name and the remaining 2 as my column name. So as I am having only one variable, I take 0, I take 1 for the rows. As I'm having two variables involving, I will follow the gray code mechanism. Now you write the address of this row value plus column value. See, row value, column value. What is row value? 0. What is column value? 0, 0. So when you combine them, you will get 000 as the address. So 000 is the address. Like this, you can fill up all the addresses, and you can convert the same into an SOP drum, and you can convert them the same into M notation also. Same whatever process you followed previously. And again remembering that your index values will be same as your cell numbers. So your cell numbers will be like 0, 1, 3, 2. Next 4, 5, 7, 6. Okay, your cell numbers will be like this: 0, 1, 3, 2, 4, 5, 7, 6. This is the sequence of cell numbers in 3 variable K map. Okay, now go with the next one, 4 variable K map. The same concept. In the case of 4 variable, first assign the 2 input variables for rows and the next 2 input variables for columns. Okay, as I'm having 2 input variables in the rows, I will follow the gray code mechanism. The same concept I will follow here also, gray code mechanism. Next, first combine the R value followed with C value. That means row value with column value. So what is row value here? 0, 0. And what is common column value here? 0, 0. So the address of first cell will be combination of row and column. Here also row and column, here also row and column. So if you combine the values of rows with columns, you will get these address values. The same concept, convert this address into, you can convert the same into SOP format by using assumptions like A bar equal to 0 and A equal to 1. So you can fill up all these values, and you can convert the same diagram into M notations. If it is SOP, you will get small m0, small m1, small m3, like that. If it is POS, you will get capital M0, capital M1, capital M3, like that you will get. Okay, whatever it may be, either small m or capital M, index values will not be changed. Why? Because the address values is same. Likewise, index values will be same either in SOP or in POS. So we can directly write the cell numbers. Why? Because index numbers and cell numbers will be equal. So this is 0th cell, 1, 3, 2. Here 4, 5, 7, 6. and again 8 will come here. 8 will get 8 here. Next here we'll get 9, 11 and 10. Then we'll get here 12, 13, 15 and 14. Okay, remember this. Okay, you'll get this as your cell numbers. Okay, what is sequence we'll get? 0, 1, 3, 2, 4, 5, 7, 6, 12, 13, 15, 14, 8, 9, 11, 10. So this will be your cell numbers for the 4 variable K-map. Okay, clear? So please learn the format of the K-map and how to label the K-map. So while labeling of K-map, remember that when you are having two input variables like this, definitely you should follow gray code mechanism. And the gray code sequence will be like 0, 0, 0, 1, 1, 1 and then 1, 0. Suppose if you are having only single variable, then no need to write gray code. Simply write 0 for one row and 1 for another row. It will be enough. Okay. So please learn how to draw the K-map and then label the K-map. Okay. But the first step initially is you need to find how many input variables are involving, and then you need to find how many cells are required. That means 2 parents are required, and then you need to draw the K-map. I'm going to draw the layout of the given, required K-map, and at last we need to label the K-map. Okay, so these are the 4 steps we have learned till now. Okay, finding how many input variables are there, and finding how many cells are required, and drawing the particular K-map and labeling the K-map. Okay, so we have learned these concepts today, and we will see the next. So how to analyze or how to group the cells or how to follow the simplification concept, we will see in the next video. Okay, so hope the today's session is understandable by you. So please practice them, learn them how to write the address values and how to analyze the labeling mechanism, right? So that it will be very clear for you. And then it is very important for us to analyze the basic steps like finding the number of cells required and drawing the layout and then labeling the K-map. Okay, we will meet in the next session. Thank you.